Hello and welcome to another lecture on formal methods. Today I'm going to start to talk a little bit about frequentist conceptions of probability and their use to analyze scientific inference. Subjective interpretations of probability and Bayesian approaches to analyzing scientific inference play a great role in the philosophical discussion about scientific inference, and that's why we've spent a lot of time over the last weeks discussing them. The prominence of subjective probability and Bayesianism in philosophy of science should not obscure the fact that outside philosophy, scientific inference is predominantly understood and modeled on a very different understanding, namely a frequentist understanding of probability and frequentist methods of statistics. So what does this even mean? We've already talked about the frequentist interpretation of probability, and frequentist approaches to scientific inference understand probabilities as a feature of events or classes or types of events, not propositions in general, but only event type objects are understood as the things that are properly understood to have probabilities. They are based on objective interpretation of probability, interpreting probability as long-run relative frequency, and we talked a little bit about what that means in lecture 5. And they utilize mathematical tools that are based on laws of large numbers. Bayes' theorem, it is of course also true of probabilities in the long-run frequency interpretation, but it does not play a big role in frequentist analyses of inference. The same is true vice versa of laws of large numbers. They can be couched in purely mathematical terms as theorems of the probability calculus, and they are so theoretically also true in the Bayesian framework, but they do not play such a prominent role there, or at least not very often. So different aspects of the probability calculus play different roles within these different frameworks. These different frameworks emphasize different aspects of the calculus, and I'm gonna try to illustrate a little bit what is behind this. So the prominence of frequentist approaches in scientific practice means that philosophers of science should have some basic understanding of how these frequentist approaches work. That said, frequentist approaches to statistics and scientific inference are not really formal methods of philosophy of science, not in the same sense as Bayesianism is a formal method in philosophy of science. So they are formal methods that are used in the sciences very much, but they are not so much used to articulate philosophical theories or philosophical analyses. So we do not discuss them because you need to apply them somehow in order to do philosophy. We discuss them in order to avoid a lopsided view of scientific inference by only looking at Bayesian approaches, and also because you have to have some basic understanding of how frequentist approaches to statistics work to understand a lot of what's going on in the actual practice of today's sciences. So, like our texts, I am going to start with a simple example, and my example is the following. The surprise egg company claims that there is one in seven surprise eggs contains a happy hippo. Most of you are probably too young to remember happy hippos, but so here you have an exemplar. So now Ada goes and buys her local supermarket's complete stock of 4,704 surprise eggs. And she's expecting to get, well, 1/7 of these eggs as containing happy hippos. She's expecting to get 672 happy hippos. She opens them all up and finds less than 600 happy hippos. Surprise indeed, but not a pleasant surprise. So the question now is, what does this result mean? Is this still a typical result that one might get from a random sample of 4,704 surprise eggs? Or does it tell us something about the company's claim that it may not be true, for example? Or about the nature of Ada's sample, that somebody has already gone through the supermarket's stock and has somehow found a way to pick out the happy hippo surprise eggs. What can we say about Ada's experience from the point of view of probability theory? Probability theory does in fact tell us that if we randomly sample surprise eggs 4,704 times, and each time the probability of getting a happy hippo is 1/7, then getting exactly 672 eggs, as Ada expects to, is in fact the single most probable number that you might get. But getting exactly 672 happy hippos is not very probable. It's only more probable than getting 670, for example. In fact, the probability of getting exactly 672 happy hippos is only about 1.66%. Now, the first important point, probability theory does allow us to calculate the theoretical probability of getting exactly k happy hippos out of 4,704 trials. And I'm not going to go through the details, but you can somehow imagine how this works. I mean, for each trial, getting a happy hippo has 1/7 probability, not getting a happy hippo has 6/7 probability. So for example, getting a happy hippo in the first egg and not getting a happy hippo in the second egg has a probability of 1/7 times 6/7. And in this way you can calculate each combination of findings, the probability of each combination of findings that you can get, and then you can add up all the combinations of results that in the end mean that you have found exactly 672 happy hippos in the 4,704 times that you've opened a surprise egg. It's a lot of different possibilities to get exactly 672 72 happy hippos, somehow distributed over those 4,704 surprise eggs. In fact, it's still quite an understatement to say that it's a lot of possibilities. The number of possibilities that you have to theoretically account for is in the order of magnitudes of 10 to the power of 836. I calculated this. But of course, there are formulae to calculate this, which I won't go into now. If you want to know the details, Google binomial distribution. So I have calculated and plotted the probabilities of getting exactly k happy hippos out of 4,704 eggs, assuming that the probability of a happy hippo in each egg is 1/7, for k's between around 590 and 750. And this is how these individual points, each of these individual points represents one of these probabilities. And here in the center, we have the probability of getting exactly 672. And you can see that it is the largest probability, though it is not very large. So this thing here is called the binomial distribution. And I'm showing it to you to make an observation. While the probability of getting exactly so-and-so happy hippos is quite small for every so-and-so, it is clear that all the probability is somehow amassed in this range around 672, around the most likely outcome, which is exactly 1/7 of 4,704. So the probability is centered around this mean value. It's important to understand what this is. It is a theoretical calculation of the probabilities that the probability calculus predicts for getting each of these results. Theoretical calculation. If Ada repeats what she does, if she buys another batch of 4,704 Easter surprise eggs, and then another batch, and we will not, and each trial she notes down the number of happy hippos that she gets, even assuming that the claim is true and there's a happy hippo in 1 in 7 surprise eggs, she will not get exactly this distribution. But the probability calculus predicts that we are allowed to expect that her distribution will resemble this graph, and it will resemble it more and more so the more experiments she does. And this is one of the laws of large numbers. Because, well, these are the theoretical probabilities, and the laws of large numbers basically imply that the more trials you make, the more likely it is that your actual frequency that you will observe will be close to the theoretically predicted frequency. So again, the laws of large number do not say that the observed frequency will approach this will approach this predicted probability, but the laws of Lord Lumber says that it is more and more probable that they will. And for very large numbers, so if you can choose how large the number of trials you want, you can have that probability, the probability that you will actually be close to, within a certain narrow range of the predicted value, get as close to 1 as possible. So back to Ada and what all this means. So we see that, okay, she is somehow entitled to expect that the probabilities, the actual probabilities, or the frequency of happy hippos in her batch will be somewhere within this range where the distribution represents most of the probability. To get a more precise grip on this so far rather vague observation, we make use of a mathematical fact. So the binomial distribution is a discrete function, and it is so it has a value for each integer here, but it doesn't have values for the real numbers between the integers. But the binomial distribution is approximated by a certain kind of continuous function called a Gaussian distribution or normal distribution. So when n is the number of trials, that is in our case 4,704, because that's each Easter egg represents a trial, and p is the probability of success in each trial, then the binomial distribution is approximated by the Gaussian distribution phi x with the theoretical mean Pn. Pn is the probability multiplied by the number. So in our case, Pn is 1/7 of 4,704. And standard deviation sigma, which is calculated like this. It's also calculated just from the probability and from the number n, from the number of trials. We're going to look into this thing called standard deviation in a moment. This is the Gaussian distribution, and don't be shocked because it looks so complicated. It's not really important for our purposes to see exactly what it is. What I want you to understand, that it is a real valued, a continuous function, and it is a bell-shaped curve. Just so it approximates this discrete distribution that we've just looked at with a bell-shaped continuous curve. And it is just characterized by two parameters, really. mu, which is just the center, where the thing is centered, and sigma, the standard deviation, which just is the parameter that decides how far spread out the distribution is. And the other things here are mathematical constants, e and pi. And now you can forget again about this whole formula. You just need to know what it looks like. And but we want to look a little bit more into this thing called standard deviation and what it is. Standard deviation is a measure of how much dispersed a sample of values is. And it doesn't just apply to these kind of normal distributions or Gaussian distributions. It can be applied to all kinds of sets of values. For a finite set of values where the mean value is this, the standard deviation is defined as this. And now I actually want you to look at a little bit at this. What we do here is we take the difference from each of the values to the mean. And then we sum up the squares of these differences. And we divide again by the number of values. So we have a sort of average. We are averaging. We're taking the average distance of each of the values from the mean. Just that we don't count the real distance, but we count the squares, and then we take the root out of it again to make it a proper average again. So it is a kind of average distance of each of the values from the mean. And we often use the small letter s for the standard deviation in an observational set of data, so-called sample standard deviation. And for the standard deviation in a theoretically predicted distribution, we often use the Greek letter sigma to indicate that we're talking about a theoretically predicted standard deviation. And when we have this nice normal distribution, a Gaussian distribution, which we know is characterized by a certain function, characterized by just two parameters, this one we have a simple formula to calculate the standard distribution from just the very basic values that we have, namely the number of trials and the probability of getting a result in each trial. So in many ways, we are looking at an example that is the simplest case of all. So we have something that has only two kinds of outcomes, namely happy hippo or no happy hippo. This is why it's called a binomial distribution, because the bi, the Greek for two, means that there's only just these two outcomes. And yeah, we have a nice symmetric distribution of the possible outcomes. And then we have this very simple way of calculating the standard distribution. And now comes another neat mathematical fact that is true for all Gaussian distributions, namely the probability of getting a result that lies anywhere within one standard deviation of the mean is about 0.68. So getting a result anywhere on this interval between Pn minus sigma and Pn plus sigma is about 68%. About 68% of all cases are here. The probability of getting result that is within two standard deviations of the mean is about 95%. So only 5% of the cases are in the green areas and the rest here. And if you look even farther, if we look at the whole thing, including the green areas, but you notice that the green area ends here, where there are 3 standard deviations from Pn, And then there's a little bit of rest of area under the curve, and the curve does not, it only approximates zero here. It never touches the x-axis of this graph. So the probability of getting a result within 3 standard deviations of the mean is always 99%. So whatever you have, whatever kind of binomial distribution you have, so you have you have a certain number of individual trials, and that you have a certain probability of getting an event for each of these trials. That's all you have to know to calculate the standard deviation, and you can already say that 99% of the results of there's 99% probability that the result will be in the range between within 3 standard deviations of the mean. So what does this mean for our example? So Ada getting anywhere between 648, so in our example, with P being 1/7 and N being 4,704, Pn is 672, as we've calculated several times now, and sigma is 24. So all you have to do to get this number is to plug the numbers into the formula, take 1/7, multiply it by 1 minus P, 6/7, and multiply that by 4,704, and take the root out of the result of that calculation, and the result you get is 24. So in our example, the standard deviation is 24. So within 1 standard deviation of the mean, that's the range between 648 and 696, lies about 68% of all the probability. And as regards 2 standard deviations, getting a result that's anywhere between 624 and 720 has a probability of 95%. And getting a result that's anywhere between 600 and 744 has 99% probability. So in that sense, the result that Ada actually got, so what I said is she got less than 600, she found less than 600 happy hippos. And that means that what that means is that if it's actually true that there's a happy hippo in 1 in 7x, then something very improbable has happened. So what Ada in fact got, say 599 happy hippos, is a result that has a probability of less than 1%, given that there is actually a happy hippo in 1 in 7x. More precisely, getting less than 600 happy hippos has a probability of 0.005, so 0.5%. Why? Because, as we said, 99% of the probability is here, within 3 sigma of the mean. So the rest of the probability that is outside of this range, in the tails, as we say, is just 1%. But half of that rest is to the right of 744, and the other half, only the other half, is to the left of 600. So getting a result that's less than 600 has only 1%, has only 0.5% probability. Okay. Now this, no, I should, before we go on, I should explain what this means in terms of the frequency interpretation. Remember this, we're working within the frequency interpretation framework. So what does this mean? It means that if the hypothesis is correct that there is 1/7 of the surprise eggs contain happy hippos, and Ada keeps doing these kinds of trials, she keeps buying batches of 4,704 Easter eggs, then in the long run she will get less than 600 sometimes, but less than 5% of the, less than 0.5% of the time. So less than once in 200 trials. So this is a 1 in 200 trials outcome, assuming that it's correct that there's a happy hippo in 1 in 7 surprise eggs. That's what that means in terms of the frequency interpretation. In the long run, if we keep doing these kinds of experiments, we will get this kind of result, a result of less than 600 only in 1 out of 200 trials, such trials as Ada has performed. Now, this is an observation that we can now use to motivate one of the most common approaches in frequentist statistics, namely null hypothesis significance testing. And the idea here would be that to conclude from this observation that either something is not right here, there isn't really one happy hippo in 1 out of 7 surprise eggs, or something very, very improbable just happened. And just to sum up the statistical relevance of Ada's observation this way. So this, if you do it like this, this is called null hypothesis significance testing, or it's called, or sometimes called, a Fisherian hypothesis testing after Ronald Fisher, a very influential and ingenious statistician, biologist from the first half, or roughly first half of the 20th century. So to be a little bit more formal about, just a little bit more formal, but I'm going with Ken Staley now and what he calls the shopping list for a Fisherian test. What do you need for a proper Fisherian hypothesis test? You need a question, a certain question that you're interested in, and then you articulate a null hypothesis that is a possible and testable answer to the question. And it's often articulated, it's often characterized, null hypothesis significance testing is characterized in such a way that it is said that the aim is to refute the null hypothesis. But that's not how Fisher put it, and that's not an ideal way of thinking about it, as refuting or as the test having any kind of aim. But you put the null hypothesis to the test, and often it's not really that you think the null hypothesis is true, but you want to show some evidence that the statistical data point into another direction. They point into the direction that the null hypothesis is not true. You of course need some data from experiment or an observation, and you need what's called a test statistics. That's some function that summarizes the data. And I'm going to talk a little bit more about this when I apply these things to our example. And you need the null distribution. That is, you need the distribution that is predicted, theoretically predicted by the null hypothesis. And then the result of the test is the so-called observed statistical significance of the data. And I'm going to explain this a little more by applying this to our example. So the question here is something like, is there a happy hippo in 1 out of 7 surprise eggs? And the null hypothesis is there is a happy hippo in 1 out of 7 surprise eggs randomly distributed over the surprise eggs that are stocked by regular supermarkets, such as the one where Ada got her sample batch. No? The data are the results of Ada's opening up all the surprise eggs in her sample batch. That's her experiment, her observation, and the data are the results. And the test statistics here is just the number of surprise eggs that contained a happy hippo. So this is an extremely simple kind of test statistics. In this case, it's just one number, namely 599. But it illustrates the importance of choosing a test statistics. For example, by we choose to summarize the results of Ada's experiment by just focusing on the number of happy hippos she got. And we are abstracting away from some other features of the result. For example, by choosing this test statistic, we decide that the order does not matter. We're not interested in the order. So if Ada starts her examination by opening the first surprise egg, and then she gets a happy hippo, and the second happy hippo, third happy hippo, and so on, all through the first 672 surprise eggs. And then in surprise egg 673, no happy hippo, and then no happy hippo anymore for the rest. Yeah? In a way, on a certain perspective, and also a certain perspective that you can make mathematically precise, this is an extremely unlikely thing to happen. But given this test statistic, where all we focus on is the number of this is fine. This is nothing out of the ordinary. In fact, this is as ordinary as it can get. 672 is definitely what the expected value. So we need some number to do the test. We need to focus on some feature of the data and ask our probability questions about this feature. And by choosing our test statistic this way, we focus on the number of eggs that we get. The null distribution here is, in our case, the theoretical binomial distribution that we calculated, or as an approximation, the Gaussian distribution, where the mean is 672. I'm sorry, there's a mistake. 672. I corrected it. And 24 as a standard deviation, as an approximation of this theoretical binomial distribution. And then the result of Ada's experiment is that the data is significant at the 0.005 level. So, okay, again on the null distribution, note that this means that you always need some kind of theoretical model for your problem, and that the null hypothesis needs to be a hypothesis of probabilistic nature such that a probability distribution can be derived from it. For null hypothesis significance testing, you need to be able to make a theoretical prediction of the distribution of possible results. Yeah? And then the result of the test is an expression of how probable it is that you would get data of this kind that you got if the null hypothesis is true. And this is called the significance level. Here I calculated, and the significance level is also called then p level or p value. That is the probability the probability of getting your observed results or a result of that kind if the null hypothesis is true. In this case, I've calculated the so-called one-tailed p-value. That means that the p-value that I give here expresses the fact that it is 0.005 probability getting the result that Ada got or even less. So we're not considering results where you get more happy hippos than within 2 standard deviations. We are just considering the possibility of getting I'm sorry, I meant 3 standard deviations. So we are we're not considering the possibility that this is not the probability of getting any result outside the area of 3 standard deviations, but we're only considering the results that are lower than 3 standard deviations away from the mean. And this represents a certain kind of interest in the problem. So I am assuming, by opting to calculate what's called the one-tailed p-value, that what we're interested in is getting at least as many happy hippos as the company claims, and that we're not interested in precision. We wouldn't be worried about getting too many happy hippos. We're interested in getting enough of them. So this is also a nice illustration of the fact that the choice between one-tailed p-value and two-tailed p-value is usually driven by our practical interest in the problem, and can only be justified in terms of our practical interest in the problem. In this case, it would be really weird to use a two-tailed p-value, two-tailed statistical test, because we're clearly the interest is in assuring a minimum number of happy hippos. So, what does this result mean? What does it mean when our statistical test delivers the result that the data is significant at the 0.005 level? The p-value is 0.005. Well, it means that either an event of probability less than 0.5% has occurred, or the null hypothesis is false. That is, there are fewer than 1 out of 7 happy hippos in supermarket batches, like the one we've sampled. So, and clearly, of course, this kind of result is supposed to send us in the direction of supporting the claim that there's something going on here. There's the significance is then interpreted as a significant observation pointing us towards the possibility that the likelihood that the hypothesis, the null hypothesis, is false. But two kinds of misunderstanding should be addressed here at the outset. This result does not mean that the probability of the null hypothesis is now less than 0.5%. First of all, we are still in a frequentist framework. And in a frequentist framework, talking about the probability of the null hypothesis makes no sense at all. Things like the null hypothesis is not the kind of thing that has a probability, because the null hypothesis being true is not an event. It's not a type of event that has a frequency. So you cannot observe like so and so many runs of the universe, and in each run of the universe, the surprise egg company produces a different number of happy hippos, and so the likelihood or the probability of that there is happy hippo in every 7th surprise egg is some value. That's not a plausible thing. It's just these kinds of things simply do not have probabilities in the frequentist framework. And frequentists, dogmatic frequentists, who think that you have to think of probabilities in terms of relative frequencies, they strictly deny that it even makes sense to attribute probabilities to hypotheses. And that's exactly what this framework is designed for, so that you don't have to do this. We don't attribute probabilities to null hypotheses. We just test them, and then we see the results. We say, okay, this is a result that is very, very unlikely if this null hypothesis is true. That's all. It might still be true, and I don't assign any probability to that, and I cannot. So that's the first thing. So it's the frequentist framework, and it doesn't make any sense to talk of the probability of the claim. Now you might say, well, okay, but what if you're not so dogmatic about the frequentist perspective? Shouldn't this say something about the probability of the hypothesis now? Now, if we wanted to ask for the probability of the hypothesis in light of the result of this result, now that we've observed this, how probable is it that that there's really one happy hippo in 7 surprise eggs? If we wanted to do that, we have to switch to the Bayesian framework. But also, even there, even in the Bayesian framework, 0.5 is definitely not the probability of the null hypothesis. It's not. That's definitely not. I mean, it may by chance be, but it's definitely not how this result can interpret it. From a Bayesian framework perspective, the significance level is a likelihood type probability. It's probability of E given H, a probability of getting this kind of result that Ada has got, given that a certain kind of hypothesis is true, namely the null hypothesis. What we're asking when you're asking about how likely is the null hypothesis now is the reverse conditional probability, the probability of H given E. And you know very well what you need to do to calculate that. You need to apply Bayes' theorem, and you would need to have a lot more input to estimate how likely the null hypothesis now is. First of all, you need some input on the prior probability of the null hypothesis, of course, but you also need likelihoods and prior probabilities for alternatives to the null hypothesis in order to calculate the unconditional probability of E by means of total probability. If you want to do that, then you have to remember in the Bayesian framework, you have to consider also, oh, okay, what's the probability of E given non-H? If the null hypothesis is not true. Now, it bears emphasizing that the null hypothesis significance testing makes no assumptions, includes no assumptions at all about alternatives to the null hypothesis. All you need is a null hypothesis, and you don't make any assumptions about, well, if it's false that the proportion of happy hippo surprise eggs is 1/7, what's going on then? Is it just a lower proportion, or is it a high proportion, or is no? How low is the proportion? We make no assumptions about this, but we would have to make some assumptions in that direction in order to estimate the probability of the null hypothesis in light of this experience by means of Bayesian framework. And more importantly, I can't emphasize this strongly enough, it's the wrong kind of conditional probability. You're getting it the wrong way around if you think that this is now the probability of the hypothesis. This is the likelihood of the data in light of the hypothesis, and not the probability of hypothesis in light of the evidence. Basically, because the null hypothesis significance testing does not make any assumptions of what the alternative to the null hypothesis might be, the thrust even of a significant result of a very low significant level is just saying that there's something going on here. There's something going on. So the null hypothesis is called the null hypothesis because it's typically a hypothesis that there's no correlation, no special correlation, no particular stuff going on. And then you find that the data are highly unlikely if there's no correlation, if there's nothing special going on. And but null hypothesis statistical testing, significance testing, never gives you any result of the kind where you can say, oh, there's something going on here and it's this. This kind of test does not enable you to say, okay, there's something going on here and the happy hippo proportion in surprise X is likely to be this or that. That's not the kind of result. It's just that, well, if the null hypothesis is true, then what just happened was very, very unlikely. There are frameworks in frequentist statistics that do contain a model for alternative hypotheses, in particular the method of Neyman-Pearson testing, which I will not go into for reasons of time. So please, I don't want you to come away with the impression that frequentists have no way of drawing any positive conclusions from data. That's not quite the case, but the most common sort of statistical method just does this, just throws some light on the null hypothesis and says that our data are very unlikely in light of the null hypothesis, and thus indicate that the null hypothesis might not be true. So, but it doesn't indicate that it is now true only with probability equaling the p-value. That would be a complete misunderstanding. Another often made misunderstanding, which is perhaps not as bad, but you can actually see it a lot of the time, that in newspaper articles, this means that there is just a 0.5% probability that the observed result is due to chance alone. That's not exactly true, because, well, what the result does roughly mean is that there's a 0.5% probability that the result is due to chance alone under the condition that the null hypothesis is true. But that's quite a different thing. And often when the data are presented this way, nobody really believes that the null hypothesis is true. It's just that it's presented in a way as proof that there's some correlation, that something going on, that something over and above the null hypothesis is going on. So it's important to know that so far as with this mathematical framework, the p-value, that is the observed statistical significance of the data, is just a value that you can calculate from the test design and the test statistics and so on. But it's important to consider that in practice, in the sciences, there are thresholds. And this is what we often mean by when we talk about p-values. So in many sciences, first of all, it's crucial to publish p-values for your experimental or observational results. Your results will not be taken seriously if you don't publish the p-values. So this is especially true in the life sciences, but also to a large degree in the social sciences. In experimental psychology and some other fields, it's conventional to mark results that are significant at a level of p that's smaller than 0.05 with an asterisk, and those that are significant at the level p smaller than 0.01, so 1%, with a double asterisk. And so, just to be sure, the smaller the p-value, the better. Yeah, A small p-value means something interesting is going on. Large p-value means this might as well just be this is so more or less ordinary observation under the assumption that the null hypothesis is true. But a small p-value means this is not really. Well, the idea is that it is, the smaller the p-value is, the closer you get to the result where you would have to say this is incompatible with the null hypothesis. Of course, when we're talking about statistical hypothesis, about probabilistic hypothesis, no result is ever completely incompatible with the hypothesis. It just gets more and more unlikely to get this kind of result. So even if there's actually one happy hippo in 7 surprise eggs, you don't find a single one in a batch of 10,000 surprise eggs. You might say, okay, that refutes it. But you could still say, that's just very, 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 very unlikely. That's the case of really, really, really bad luck. So, because there's no such thing as actually really refuting the null hypothesis, this is as close as we get. The closest we can get to having these kinds of results is having small p-values. The smaller the p-value, the more interesting, the more relevant the data. So in different fields, certain p-values mark what counts as a minimum of empirical support that a result must have in order to be acceptable, to be worthy of serious consideration. So if you want to claim, for example, that a certain drug is effective, the null hypothesis is that it's not effective, and you have to have data that at least have a minimum, a maximum that, okay, so the minimum of empirical support for your claim that that the drug is effective is equivalent to a maximum of acceptable p-value. So the p-value must at most be 0.045. This is a very common level. So if you say, okay, our results are the significance level is 0.06, it's conventionally regarded as not significant. So this sort of what in Fisher's methodology originally is just is a continuous value, just one out of many features of a set of data, has turned into a threshold value where something is either statistically significant or not statistically significant. And statistically significant means a p-value smaller than 0.05. That's the next bullet point. And sometimes you also have the convention that statistically highly significant means smaller than 0.001. So 1 per thousand, probability of 1 per thousand. Yeah, and many scientific journals now refuse to even publish results that are not statistically significant in this sense. That is that with p-value higher than 0.05. And in some fields the conventions are more stringent, and there's a lower maximum significance level that is permitted. So these kinds of conventions are mostly what are related to the widespread criticisms of the methodology of null hypothesis significance testing. And I would like to emphasize that the problem is not so much with the test method itself. The test method does deliver a certain interesting kind of feature of the data. It is inherently limited in the sense that there's so much more you want to know about the data than just whether they are statistically or the level of statistical significance. But it is an interesting feature. If there are problems with null hypothesis significance testing, then these are mostly related to the prominence and the focus on the significance level that the practices and conventions of many scientific disciplines have begun to exhibit. And so one of those criticisms is that, well, as I already said, the meaning of p-values is often misinterpreted and misunderstood, even by researchers. There are empirical studies of this where you send out surveys to researchers and you ask them some questions about p-values, and it's horrifying how that the kinds of things that some that people get wrong, actually. So the worst such misunderstanding is to interpret the p-value as the probability of the null hypothesis, which is simply a fallacy of reversing the conditional probability, at the very least, and combined with a number of other fallacies of misunderstanding the probability framework that you're working with. And another is also to interpret a non-significant result as a corroboration of the null hypothesis. So if you don't get a significant result, then you think that, oh, well, then the null hypothesis is probably true, which is also not a valid inference. A second criticism is that excessive focus on statistical significance is highly misleading, and it obscures the relevance of other dimensions of the data. And one important aspect of this is that statistical significance says nothing about effect sizes. So a paper, for example, might report a statistically significant reduction of cholesterol levels in patients' blood as a result of administering a certain experimental treatment. But the fact that in the study, so the null hypothesis would then be, well, administering this drug has no effect on cholesterol level, and then you notice that, the distribution of cholesterol levels between the experimental group and the control group, there is a statistically significant difference between the distributions there, but it does not mean, so it means that this is kind of a difference in distribution that is unlikely to have come about by chance. But given that the null hypothesis is true, but it could still be that the reduction of cholesterol that is affected by this drug is only very, very small. It's minuscule. If it's just very reliably produced by administering this drug, that will lead to a statistically significant result, and you can have a nice publication, and you can sort of market this drug and say, well, there is a statistically significant reduction of cholesterol level, but this has nothing about by how much. And if you hear significant, so the part of this criticism has to do with the focus on one particular variable, and that just we should talk more about other variables such as effect sizes. And another a part of this criticism is also that the terminology of significance is in itself misleading, because a statistically significant result does not automatically mean a practically significant or even scientifically significant result in the ordinary sense of the word. And then there's the thing that the conventions pertaining to null hypothesis statistical significance testing contribute to publication bias. So if published results are selected by significance level, it means that negative results are suppressed or forgotten. So when you do a study and you don't get a significant you don't get a significance level of 5% or lower, then you cannot publish it. And it just lands in the file drawer, as it is often called. And this can be, so that's the so-called file drawer problem. This can be expected to result in waste of resources because, well, somebody else is getting interested in the same kind of question and he looks, okay, has anybody ever done this experiment and tried that? And you look into the published literature and say, no, apparently not. And you do this again and again and again and again. And also it can lead to, which is perhaps even more pernicious, it can lead to the fact that the published research record misrepresents the totality of research results, because lots of the research results are negative in the way that you don't find a significant correlation, you don't find a significant effect. The null hypothesis, the data is quite compatible with the null hypothesis, but that's not no result. That's a result. So, for example, in the medical literature or in the literature on medical interventions, this may result in the fact that the totality of published literature overestimates the effectiveness of medical interventions, because all the trials where medical interventions have been tried and there was no interesting result, they just don't end up not being published because it's regarded as a not significant result. And this pertains to the totality of, well, the state of research in biomedical science as a whole, but it can also pertain to studies on a particular kind of intervention. When you have just some studies produce a significant result and they then get published, but there were also lots of other studies where no significant result was observed and you never learn about them because they do not get published. So this has gradually been recognized as a problem and is being addressed in certain ways, for example, by requiring medical trials to be pre-registered. So before you start the trial, you have to register with a certain official registry that you are going to start this trial, and then so that people can in principle see all those trials that have been conducted but were never published or were never published with a prestigious journal. And the last thing that is kind of currently a very much discussed problem is that the tools of null hypothesis significance testing in combination with these problematic conventions give rise to questionable research practices such as p-hacking. So p-hacking refers to a range of certain techniques of getting results with publishable p-values out of your data set. One way is, of course, when you have a certain set of diverse data and you don't specify in advance what is the question that you are looking for in this data set. And instead, you look at the data set and you try to find all kinds of correlations that you may be able to see within your data set. Then the method of analyzing supposedly significant features of the data by means of fissuring, significant testing becomes trivialized in a way. Note that the threshold level of 0.05, that is 5% threshold level, which is widely regarded as sort of the maximally acceptable significance level. That just means 1 in 20. So given that the hypothesis, the null hypothesis is true, you would still get results of that kind in 1 in 20 cases. So if you have a data set and you just blindly ask 40 different kinds of questions about this data set, but all kinds of correlations that could be there or could not be there. Even if in all these cases really, in fact, the null hypothesis is true. That is, there's no actual basis in the actual probabilities at work for these correlations or so. It is unlikely that you will not find a statistically significant correlation in 1 or 2 of the questions that you ask. Because if you ask 40 questions and you get, and your aim is just a significance level of 5%, well, then there may be 2 of the questions that you asked may be answered in the way that you desire, just by chance. So this is this was very nicely, this is also called the multiple comparisons problem. This was very nicely illustrated by Randall Munro, the genius behind the webcomic XKCD. Very highly recommended, xkcd.com. And here's the comic. And of course, I have to focus, to zoom in a little bit. So, jelly beans cause acne. Scientists investigate. The scientists investigate and they say, oh, we found no link between jelly beans and acne. The p-value is larger than 0.005. That means the null hypothesis is that there's no correlation between eating jelly beans and getting acne, and the data that you get is significant at a level larger than 0.005. So it's completely compatible, and it's what you expect if there's no correlation. Yeah. So scientists say, or this guy says, that settles that. But then she comes and says, I hear it's only a certain color of jelly beans that causes it. Scientists! So the scientists have to investigate again. And now they say, we found no link between purple jelly beans and acne. Again, p-value is larger than 0.005. And again and again, so they do this with brown jelly beans, pink jelly beans, blue jelly beans, teal jelly beans, whatever, until here. Oh, we found a link between green jelly beans and acne. And now there the p-value is smaller than 0.05. And they go on with the other colors and they don't find a statistically significant correlation. And in the end, the news story, green jelly beans linked to acne. Only 5% chance of coincidence. Well, in a certain theoretical sense, we see that this is true. It is true that in the individual trial, given that under the assumption that there's no link, between green jelly beans and acne, the data that was produced by this trial has only a probability of 0.05 or less of occurring. But if you look at all the trials they made, so only 1 out of 20 cases they would get data like this. But they did exactly 20 such trials. And hence, it's not so surprising, and it is what you would, as a matter of fact, it's what you would expect. It's the expected outcome of getting 20 of such trials. Okay. I'll end with this as a cautionary note about p-values and null hypothesis significance testing. And I emphasize again, it's really more about the use and the monomaniac use of these kinds of p-values and significant monomaniac attention to significance levels and the pernicious kinds of conventions used by the scientific community related to significance testing. It's not that the method in and by itself is in any way compromised. It is limited in what it can say about a certain set of data, but it is perfectly suited to the frequentist framework. So, okay, I look forward to seeing you soon.